Constant acceleration equations are so common that a special set of equations has been derived for dealing with them. When the acceleration is constant, the average acceleration and instantaneous acceleration are equal, as we saw in previous videos, and hence we can equate average and instantaneous acceleration equations. Therefore we can write instantaneous acceleration, A, is equal to average acceleration, A, AVG, which is equal to V minus V naught, divided by t minus 0. Here v naught is the velocity at time t equal to 0, and v is the velocity at any later time t. We can rewrite this equation as v is equal to v naught plus a into t. As a check, note that this equation reduces to v is equal to v naught for t equals 0, as it must. As a further check, taking derivative of this equation gives dv by dt is equal to dv naught by dt plus d by dt of a into t. Here, the initial velocity v naught and the acceleration of the particle a are constant. Therefore the equation reduces to dv by dt is equal to a, which is the definition of acceleration, a. From the equation we see that the velocity is linearly dependent on time. A linear equation is an algebraic equation in which each term is either a constant or the product of a constant and the first power of a single variable. A linear equation always represents a straight line. If we plot the graph of this equation, it will be as follows. We will now derive the equation for the displacement of the particle. With few modifications, the equation for average velocity can be written as VAVG is equal to x minus x naught divided by t minus 0, where x naught is the position of the particle at t equals 0, and VAVG is the average velocity between t equals 0 and a later time t. For a linear velocity function, the average velocity over any time interval, say, from t equals 0 to a later time t, is the average of the velocity at the beginning of the interval and the velocity at the end of the interval. In our case, velocity at the beginning of the interval, that is at t equal to 0, is v naught, and velocity at the end of the interval, at any later time t, is v. For the interval from t equals 0 to the later time t, then, the average velocity is given by VAVG is equal to v naught plus v divided by 2. Substituting the equation, v is equal to v naught plus a into t. In the above equation, we get VAVG is equal to v naught plus a into t divided by 2. From the first equation we get VAVG is equal to x minus x naught divided by t. Therefore, x minus x naught is equal to VAVG into t. Substituting VAVG in above equation, we get x minus x naught is equal to v naught into t plus a t square divided by 2.